Hello, everyone, and welcome to our Wednesday sessions. We're going to give everybody a few more minutes to get admitted, and then we will begin. All right, so we are going to go ahead and get started. Today, we're excited to welcome Dr. Carlos Flores, a quantum algorithm engineer and researcher at Kipu Quantum. He works at the intersection of quantum computing, artificial intelligence, and machine learning with a particular focus on developing practical quantum solutions for real-world industrial challenges. His research includes quantum machine learning, feature extraction, optimization, and hybrid approaches that combine quantum and classical computing. At Kipu, Carlos contributes to research aimed at moving quantum technology beyond experimentation and towards meaningful industrial usefulness. His recent work has explored how quantum processors can enhance machine learning models while addressing the practical challenges of applying quantum methods at scale. So please join me in welcoming Dr. Carlos Flores, and I'm going to let you take it from here.
Okay, thank you so much, Rachel. So let me share the screen if you want. We can start. Okay, just let me know if you can see everything. It's okay?
Yes.
Okay. So well, as Rachel mentioned, I studied physics, is my main background, but I did also my master degree in data science and also my PhD on quantum machine learning, but more related in the pre-steps of the data, like quantum feature extraction, quantum feature selection, and also quantum reasoning, right? So in this talk, I'll be talking about quantum combinatorial reasoning for large language models, that I think is a topic that is now quite fire, right? It's interesting of everyone. Yep. I will do a small presentation. Also, I work for Kipu Quantum, that we are a software company that we deliver software solutions, and quantum machine learning is my main topic. But we also do quantum optimization things and whatever. So if you want to see all the products and all the things that we can do, you can visit the website. Probably at the end of this talk, I will show you more or less how is the website and what you can start working on. And yeah, that's all. So in this presentation, we'll cover 5 main areas, because the last one is the Kipu Quantum Hub, as I mentioned. So first of all, we'll talk about the theory of chain of thoughts, more what is reasoning and how the LLMs are working, and the different ways that we can ask a question and whatever. Then we'll see the methodology that we have created based on the Hubo formulation. Hubo is high order unconstrained binary optimization problem. That is an extension from Cubo. We'll see it after that, but well, yeah. Is the way we encode the information in a Hubo, and then we solve this problem by using simulated annealers, that it is the classical approximation, but also bias field DCQO, that it's a purely quantum hardware software that we created in Kipu Quantum. After that, we'll see the results in the most important data set that I think LLMs can be tried. And this big bench extra hard, we'll explain a little bit the 3 main data sets that we are working, and then we'll see the results about different LLMs and the real hardware and the classical one. And in the last 2 slides, we'll see how we can save energy. That is a little bit tricky because the backend at the end is still expensive, but we can save energy in the sense of saving tokens. We are not spending too much. And then a new extension that we are working out, in this case, it's overcloud Opus 4.8, which is a very good indicator that we are doing the things well, right? Because even now the reasoning or the inner reasoning models are increasing and are doing it better. We can also use this technology or this quantum reasoning approximation to solve and to improve a little bit the accuracy. So, okay, and just in order to say, at the end of each of these areas, we can save 2 or 3 minutes in some questions. And at the end of the whole presentation, we can do a more deep question time, okay? So let's start. Okay, so first of all, we will explain how more or less the reasonings are in the LLMs at the beginning, how now are getting. At the beginning, we had this idea of 0 shot, okay? So we only ask 1 question and an instruction. So with these 2 things, the LLM needs to answer with no context, with no other things or explanation that can bias this, right? So these kind of questions that are 0 shot are directly solved by the model, right? So the model is trained and you only have this question in this context and you obtain a a solution. So you are not retraining the LLM, right? Which is the strong point. So generalize good, right? And from the same template, you can have different solutions depending on one parameter that is temperature. But at the end, you have the solution by default from the model. So this can kind of evaluate directly the model itself with not understanding the context. Okay. The weak point, so is sensitivity to instructions. I mean, sometimes it's biased about that. And also, as you can see, if you change the temperature, you can obtain different solutions or even different answers based on the same question, which is this kind of hallucination or whatever that the LLM has. So what is one shot? One shot is the same as the zero shot, but you can add an example. So you can give context to the LLM in order to solve this kind of problems. This obviously expends more tokens, which is a bad thing, and also can be biased because you are adding only one or two context to them. If these answers are bad done, at the end, the new one will be also bad done, right? So, which is the strong point? Now the answers should be more similar, not quite different. That can be in the zero shot by changing the temperature. And the weak point can be biased because if your example is bad, so also your solution will be bad. How the LLMs works or reason, because this is the question, the main question, where we introduce this chain of thoughts as the new paradigm. Okay, so the silent inference is where all LLMs works. So you have a token and the next token is based on the last tokens that you have produced. So it's the probability of adding a new token. This is the way you produce the answer. This is how the LLM works. But you can decompose this into smaller steps that we can say that like reasons, okay? So as we can see here, there is no internal symbolic reasoning. So you only reproduce the next step based on the other ones, on the last ones, and the answer is a single step. So what can happen here and which are the main or the typical failures? So we have a premature commitment to a wrong answer at encoding times. We can skip through problems that look obvious but are not. You can hallucinate. This is the most common one or the most famous one, because probably in the local side of this sentence is okay, but in the global one is not. And as the most important is the probability of the last token and then is being decreasing over the past ones, you can do it very well in the middle, but you are forgetting or you are not having memory from the other ones, right? And obviously this is also a sensitivity to wording because small prompts change and flip the output, obviously. So then in 2022, they introduced this chain of thoughts. So it's very simple. You only need to ask to the LLM, think step by step, which means this. Before having a final answer, you can have small places or small goals that you can have. So each one of these goals are the reasons, right? So we can decompose the final solution into the steps that converge to the final one. So that's good because we can use this to see where exactly the chain of thoughts starts to fail, right? They start failing. And this is more or less how it works. So, for example, you can have one query, all zero shots, because we are only asking the query by itself. That is the question. And we can see that if we change the parameter of the temperature, that can say if you can do it similar or more different, you can have a different family of solutions. You can see that you can obtain, for example, this chain of thoughts of 5 reasons and converts to A, another 5 reasons that also converts to A, only 3 ones that converts to A, and you can have different paths to converge to A. But in some of them, it changes because, as I tell you, when you are doing zero shots, your LLM can sometimes give you one answer or some others give you another one, right? If you ask several times, you will have something like this. So there are some strategies based on these aggregation problems, that is the self-consistency and the voting based, that we can explain it here. The majority vote is only picking the one that has been delivered more times. So if we have asked 20 times, we have 12A, so A is the final question, A is the final answer. And the self-consistency is more or less the same, but you also penalize the ones that are exactly the same. So if you have a chain of thought that is very similar to another one, you can discard it or weight it in a less way, right? So it's also a kind of both systems, but also see the reasons how they construct it and everything. Which is our idea? Okay, our main goal is to use all these reasons that you can see here and to produce something that can give us value, right? So it was a paper before ours, that is the SNCAN in 2024, that tries to codify all this information into a cubo. Okay, the cubo is this, that it's a quadratic and constrained binary optimization, where you can add in the one body term the importance of the variable, and in the two body terms, the redundancy of the variable. So in this case will be how important is one reason, and in the other, you can say more or less how similar, or all the things that you can consider that can be penalized, right? At the end, the solution gives you 0 or 1 in order if it's included or not included, right, when you solved it. So what they do is to ask several times the same query, and they try to build this Hugo problem, or Kubo problem in this case, based on some parameters or some things that now I will explain it. But basically, it's based on frequency. And at the end, so you select the most consistent ones. Which are the limitations, and why then we will extend it. Kubo only have two body correlations, so only can compare two reasons if they are or not similar or whatever, but can't do more than two. So if you want to relate reasons that appears in pairs, it's okay, but if you want to relate reasons that appear in triplets or quadrets, it's more different, okay? Yeah, let's see how we define our proposal. Our proposal is not only limited the problem into the two body terms, but also extend it in multi-body terms, okay? So this is a little bit more complicated, and is where quantum hardware can help the more, because the Kubo problems are mostly very well solved in classical algorithms, but for three-body, four-body, or multi-body, they start to struggle, right? Because they don't work natively in this sense. But quantum, yes, quantum does. So this is very interesting because you can encode this information into a Hamiltonian, and if you can evolve this Hamiltonian, even it's two-body, one-body, three-body, or five-body, you can solve the problem in theory, okay? There are other problems like noise and whatever that can struggle also, but at the end, in the theory, you can tackle this problem naturally, right? This is why we consider that it's very, very interesting to do this. Also, we'll see when we want to solve these Hugo problems with a classical method like simulated annealers, we need to decompose it into Q. So at the end, we are encoding three-body informations, but only taking into account two-body terms, okay? This we'll see more in depth, but it's more or less this is the idea, right? Okay, do you have some questions until here? Because it's the core of the talk, so I think it's important to understand everything well.
Yeah, so if anybody has questions they'd like to ask for the moment right now, you can type them in Discord and I'll ask them for you. And I believe he's going to stop and give this opportunity a few more times throughout his talk. And then at the end, of course, we can have more discussion. I do have a question here. It says, why does Kubo have a two-body correlation?
Yeah, that's it. Because you can, at the end, this is an optimization problem where you want to minimize the energy, right? So if you encode the information in coefficients, here, for example, is the Q. Let's see, like, is how frequent is a reason over the 20 questions that we have asked. So we repeat 20 times the same question. We will explain this more in the methodology. This is only the one body, right? Is the importance, how many times you repeat this. But in this other one is how many times two questions appears together, right? And we need to see if appears together because they are very similar or because they are very important to do it together. So you are giving here an opportunity to not only judging the majority vote of the reason, but also the co-occurrence of both, right? And let's see after that how we define the coefficients. But if you do it in a clever way, you are penalizing the ones that are very similar, and you are increasing the importance to include both when they are not the same and they appear several times, right?
Okay, thank you for that. Another question we have is, what if the output is partially correct and partially hallucinated?
This is a very good question. The thing is that we don't know, right? Because by doing this, we don't know which answer is the good one. That's the problem. The main problem is that when a question is very difficult, or is, for example, for causality or humor, that the LLMs doesn't know really, we don't know the answer. And we need to require experts to see, okay, these ones are the correct ones. So this method is totally unsupervised. So we are only paying attention on the reasons, but not on the answers. We don't use the answers at all. So this could be good or worse, but at the end, as we have some interesting data sets that we can test it by only doing majority vote, by only doing zero shot, or by using our reasoning mode, and we see that at the end we increase a little bit the performance. It's not a lot, when in some cases it's a lot, but it's that we are increasing. So now we need to believe that this method is better than another, because in the future we want to know the answer, right? We won't know, or we never could know if the solution is good or no. But I prefer to pick this reasoning mode than another one, because normally increase the accuracy. So this is more or less the sense of doing quantum reasoning.
Okay. We'll do one more question and then let you continue on with your talk. Is the advantage mainly due to quantum computing, or does the Hugo formulation itself improve the reasoning process?
This is another very good question. Nowadays, we consider that is the formulation. The Hugo formulation is the most important things. At the end, we will see it. But the good thing is that the quantum computers, if the question is more complicated, we will need more than 3 body terms, right? If we need more than 3 body terms here, we need to go for 4, 5, or 6 body terms. The simulated annealers can solve it, or other solvers struggles to solve it. And quantum at least can tackle the problem naturally. So it's there where the importance of the quantum computer can be. The formulation is good, that it's working. And if it's working for 3 body, we believe that it's working for 4 or 5 body. And in this moment, we need quantum computer to solve it, right? So here is more about the methodology, but in the future, we believe that the quantum computers are the naturally solvers that we should use, right? So we continue, right? Okay, now I'm gonna explain a little bit how to build this Hugo problem, and then how to transform it in a Hamiltonian, and yeah, let's start. Okay, this is more or less the main map route, how we work. We have an initial prompt, can be a difficult or simple question. And what we do is to ask several times the same LLM or different LLM, because we can combine LLMs in this case. And what we have is for each answer, a subset of reasons, right? So at the end, we can compute and create a graph problem that it's translated into a Hugo formulation problem. And we use a quantum solver or a classical solver to obtain the reasons that are more important, right? So at the end, with these selective reasons and the query, not adding information on how to solve it, just adding the reasons that we consider are the most interesting ones, we re-ask the LLM and we obtain the final answer. Okay? So first step is sampling, as we have mentioned. We generate n, in this case, for example, is 20 times the same query, and we keep all the reasons in a set of reasons. Then this can be also changed because we have temperature. If the temperature is 1, the reasons should be more diverse. And if it's close to 0, it's more deterministic, the answer. And then we can restrict also the token consuming or the top P more important reasons or whatever. So we can more or less ask to the LLM whatever we want. For example, be diverse, don't do more than 10 reasons per query, and try to minimize the number of tokens that we want to solve. This creates reasons that are not reasonable big, more or less very short reasons, which is very important to have this because we want to improve it with the less consumption, right? And okay, and at the end we have this set of reasons. What we do then? We do this deduplication thing. So we embed which reasons are more or less the same by using an old MPNet base that is a NLP transformation model. And then we can compare if a reason, given a reason, if it's similar or not to other. If it's similar, we save only one of them and we count like two times the reason appears, right? So at the end, what we can do with this is to keep the distinct reasons, all of them, and the number of times that each reason has appeared, okay, in these 20 questions. So that once we create this Hugo problem in this case, we need to transform it by using this transformation that, because at the beginning is the binary basis, but we need to be in the Hamiltonian basis, right? It's the spin glass basis. And we need to change x by z. So now if x is 0 or 1, z is -1 or 1, depending on the spin up or down, right? In the final solution. And the Ising form is like this. And these weights, we'll see now how we want to construct it. Okay, The linear coefficients. The linear coefficients are very simple and are also only based on frequency. So first of all, what is P is the probability to appearance in 20 times, right? If we have 20 questions and a reason appears 17, so we have 17 under 20, right? And then we have the risk, that is the variance itself. Because if one reason appears several times, always, probably is not that important, probably is naive, it's a reason that can be easily tracked for the next question, the next time question. But if it appears more or less half of the times, is the best moment to obtain it, right? Because it's like sometimes it's important, but it's not always appearing like that. And if it didn't appear anything, so it's another time not important. As we want to minimize the energy, we put a minus parameter of the probability of this reason to appear, plus another parameter alpha with the risk. So the risk increase the energy and the probability decrease the energy. So we want a probability high, so this range, high probability, and a small variance. And we don't want, something that is more or less in the half of the times, right? Okay, the pair coefficients is more or less the same, but based on co-occurrency, right? So it's how many times two reasons appears together in the whole, minus the probability of appearing independently. So, for example, if two reasons appears 5 times together and by separate they appears 7 times each one, is good, right? Because the multiplication of 7 divided by 20 to the square and 5 divided by 20 is much less, right? So we want to appear a lot of times together, but not appearing separated several times. And then we can standardize this just in order to see which is the mean of the times of two reasons appears. That is not pretty normal. So for example, the mean of two reasons appearing together could be 3 times over the 20 questions. And if it's less than this, we penalize. And if it's more than this, these pairs are good and minimize the energy, right? Because here we want here to be positive or higher than the mean. So this is positive and this decrease the energy, right? And what we don't want, that two reasons are too similar. So we compute also the cosinus similarity from two reasons. This penalize and this minimize the energy. So this is more or less the idea. You can see that we use the set score. It's based on that. We want only paying attention on the ones that are above the mean occurrency, right? So yeah, the idea is more or less this. It's like rare but significant occurrences are not drawn by frequency ones. And the triplet is exactly the same as the two body correlations, but with 3. It's the triplet occurrency, right? This is how we compute the triple correlation. As you can see, it's exactly the same. This is the probability of appearing 3 reasons together minus the probability of appearing each one by separated. Then we standardize with the set score, and then we apply the same coefficients, that is this penalize and this penalize the energy. This similarity is the mean of the similarity by pairs. The similarity of first to the second plus the similarity of first to the third plus similarity of the second to the third divided by 3, right? And at the end, we have this Hamiltonian. Well, this is the Hugo problem, and this is the set spin basis because we need to do a change of basis. But at the end, we have this Hamiltonian that we want to minimize, right? So the prime coefficients are linear combination, W1, W, and IJK, produced by the base change. Because we need to change it. This will change. This is how we formulate the problem, and then we need to do this base change, okay? Which is very important because we need a landscape of energy to solve it in a quantum computer. Okay, let's explain a little bit what's the problem of using classical solvers in Hugos. Is that simulated annealers are restricted to QUBO. Normally, there are some strategies to do it with an exactly 3-body correlation part, but it's not normal and it's very costly, okay, if you want to solve it. So this is when simulated annealers starts to struggle. So what we need to do, we need to transform this last side, that is the 3-body occurrency or the 3-body terms, to a 2-body formulation. What we do is to keep this variable, this coefficient, that is the coefficient that we have encoded all the information, and using the sum of the pairs by separated, minus the constant. So this transforms the 3-body correlations into a 2-body ones, where we can solve as a cubo. Now this changed because we need to add here this constant and these coefficients change it, but at the end, more or less the information is the same, but is not naturally solved in a three-body term, right? So we need to decompose it. Probably in this decomposition, we lose information about the three-body couplings. Okay, which is the thing that is very interesting in quantum solvers. So our bias field is CQO, that you can see the paper. It's also in our website. I will share with you the link and how to go to see all the papers that we have. Tackles directly this problem. So you can embed all this information into a real K-body problem. So it's a real Hubo problem, not decomposed into a Cubo. And this is very important because you can solve K-body Hamiltonians natively with no quadratic reduction. You can map, as we say, with this change of basis, and then if we let the Hamiltonian evolve by applying counter-diabatic protocols, that it's, well, this is another talk. If you want, we can discuss a little bit how it works. But in essence, what we do is to try to minimize the energy of a Hamiltonian. And if we can encode very well this Hamiltonian and we let it evolve with unlimited time, this is the adiabatic theory, we can obtain the ground state. But as we don't have limited time, we need to apply counter-diabatic protocols in order to do it a little bit faster. And bias field is the new thing that they introduces that helps you with a warm starting point to converge to the final energy, right? To the ground state at least. So you can see, for example, in the first iteration, we obtain this Gaussian here, this kind of Boltzmann distribution. And in the first iteration, we moved a little bit further to the left, trying to obtain better solutions. And the second one here more or less does the same as the first one, so we could keep the first iteration, right? Okay, how we pick at the end the reasons. So let's come back here. What we pick is only the 25% lowest bit strings that we have generated in our solver, right? Because we have, for example, 1,000 number of shots. This shot, each one gives you a solution, and you can sample the energy distribution of these solutions that we sample. So we can keep only the last one. This could be applying the best solution, the ground state, and we can keep only these reason selections. But I think it's not the best idea because we have a human failure by encoding this into a Hamiltonian, right? So it's more interesting to keep all the families of solutions that are close to the ground state, but probably are not exactly the ground state, but are also interesting. So what we compute here is to pick all these B strings that are in the 25% lowest energy range and compute about system, right? It's like if the reason 2, how many times appears in these 250 solutions. Because the B string is a set of, for example, if we have 30 reasons, it's a B string of length 30 with zeros or ones. 0 means you don't pick it, and 1 means you pick it. So you can sum the times of this reason has been selected in all these solutions. So for example, in the 98% of the times, the reason 2 has appeared in all these families, right? In all these B strings. And you can compute this and do a ranking of most important reasons. So here you can see, for example, we can select which is the threshold. Let's see, 50% is the simpler one. And we keep the ones that are above the 50%, and we discard the ones that are about down this threshold. And this is more or less the technology that we use to select which reasons are interesting and which are not. Also, there's things that can be tunable, right? We can do kind of this threshold, set it like a hyperparam selection, but at the end, this is not a machine learning tool. We don't know exactly the answer, so we don't know if this selection is good or not. So we can play a little bit. We can be more restrictive by like putting this threshold in 80%, we will keep less reasons, or applying only 20%, and we can keep the whole reasons. So you can be restrictive by changing this. We'll see this in an example, then in a demo that I have created, but more or less this is the idea. So let's try to do a small report on how this works. First of all, we have a query, right? And we repeat this question to an LLM or to a multiple LLMs, but let's see only one LLM, n times, for example, 20 times. So at the end, we will have a diverse set of reasons that we have generated in all these n samples that we have done. We can extract all these reasons and we can deduplicate it by using this NLP model and using the cosinus similarity. So if two reasons are similar, we convert this both in only one, and we count that is 2 times this reason in the whole process, right? Then we compute all the coefficients that we have explained, that is the 1-body, 2-body, and 3-body coefficients based on frequency, but also in similarity of the reasons. Then we can build this Hamiltonian based on these coefficients that we have created. We can solve it by using simulated annealers or bias field DCQO. And we apply this kind of method to select the low energy configurations and compute if this reason has to be included or not, okay? Then we select the best reasons, for example, 10 from 20 reasons, and we re-ask the same query, but by using only these 10 reasons. And at the end, we have a final answer, okay? Let's see an example, for example. In this case, we have sampled 20 times this zero-shot question, who will win the FIFA World Cup 2026, okay? So we have 20 independent cloud calls. It's cloud 4.8 because it's the one that has internet and can see the actual behavior. And we have these reasons. This is all the reasons that we have. For example, you can see some examples of them. The hosting moves to USA, Canada, and Mexico. This is an important or not, but could be an important or not reason, right? So we sample the whole reasons, we put it together, we decompose them, then we do the similarity and we create the Hamiltonian, and at the end, what we can do is this. Here you can see the number of counts of each reason has been appeared, okay? And at the end, you can see that we select 15 reasons. In this case, it's the same as counting only the ones that are above 4, but this limit is set by the quantum computer or the simulated annealers threshold. We don't decide, okay, we are going to include above 3. No, this is decided by solving the Hamiltonian, right? And trying to go for the minimization of the energy that we have created. And at the end, the answer is Spain. I mean, I'm from Spain, but it's not because this is what the LLM said, right? So yes, we finish here the methodology. So if you have any question, probably you should have. So it's important also to answer them.
All right, yes. So we do have a question here. It says, many quantum optimization methods demonstrate improvements on synthetic benchmarks. Have you evaluated BF-DCQO on real-world combinatorial optimization problems? And what characteristics of those problems make the native higher-order Hamiltonian representation significantly outperform Kubo-based approaches?
Yeah. I mean, this is a good question. At the end, we have a limitation, right? The main limitation is the number of qubits. So I think the quantum solvers could try to solve everything because, well, all the problems that are discrete in this case, we can solve optimization problems that are continuous so far. But it's limited mainly in the number of qubits. I mean, the good thing here is that this multibody sometimes creates you a better benchmark, sometimes not. You can see the papers that I will share to you. So if you want to see more in depth all this technology and the suitable cases, right? But at the end, we can only use synthetic, as you said, because it's 156 qubits. I mean, this is for IBM. There are other hardwares like D-Wave that has more, but it's more complicated because there are qubits that are physical qubits and then logical qubits, and we are not using at the end these 4,000 or 5,000 that they said. So we are limited mostly in the number of qubits now, which means the number of variables because we encode 1 qubit per variable normally. And also the constraints, because if you need to add constraints in the optimization problem, you should like save some qubits to add these constraints. So at the end, we have less variables also.
Okay. I have a question that was asked previously, and it's saying, in this case, how is the Kubo-Hubo formulation done? I'm not sure what they're referencing. Do you have a point of reference for that question?
How is done? You mean how is the coefficients compute or
the question just says, in this case, how is the Kubo-Hubo formulation done?
Yes, I mean, okay, you can see here the coefficients, that is the WWIJ and WIJK, and here you can see how it's built. Let's pick the one body. The one body is built by using this, which is a parameter with the probability of appearance of a single reason, and then is the risk, which is the variance. So this tries to maximize the energy and this tries to minimize the energy. So we let evolve the Hamiltonian in order to solve this Kubo formulation at the end, or Hubo formulation at the end, which tries to minimize the energy of this Hamiltonian that we have created. So how we build The problem is that it suits perfectly to the quantum hardware, right? Because we have exactly this in the nature. I mean, the nature tries to go for the ground state to minimize the energy. And if we can encode perfectly this information into a quantum computer, in our case, for example, a digital hardware like IBM, you only need to decompose this problem that is a Hamiltonian into gates. That is a problem called trotterization. That is not easy also to do it. But if you do it in a proper way, theoretically, you will solve the problem, right? So how we build it, we do this Hamiltonian and we try to mimic this Hamiltonian in a digital hardware, which includes gates and not time evolution, but you can more or less obtain a very precisely comparison, right?
All right, I'm going to give you one more question so that we still have time for you to continue your chat. So this last question is, compared to a standard QAOA mixer Hamiltonian, how different is the design when you are specifically building a circuit to handle language model logic and combinatorial constraints?
Yep. That's exactly why we use bias field DCQ. You can see the first iteration is purely QAOA. We can use bias field DCQ in order to solve it or go to a better ground state or trying to have a better family, because at the end we keep the 25% of the lowest energy bit strings. So the thing is, you build this Hamiltonian and then you solve it. You can do QAOA perfectly, but we extend this with bias field DCQ, but it's an extension. You can have iterations and trying to move further to the left side, right, to the family with the lower energies. Okay, so I think I continue. Okay, let's see the results. Try to see it fast because I want to do also a demonstration and a small demonstration. Okay, so just to give you a little bit of concept, we used 3 datasets: causal understanding, disambiguation, and New York City conceptual combination. Sorry, this one is based on if there's a causality between 2 reasons. We'll see an example. Then this disambiguation gives you if a pronoun or a noun is referred to another one, that it's a little bit of language understanding is the main goal. And the last one is trying to see which is the funniest caption of given a situation, right? So it's trying to understand the humor. These are the 3 ways that the LLMs struggles a lot, right? Because they try to be kind of solving the problem, understanding exactly the situation, and humor is, for example, based on the opposite. It's trying to see, okay, this is impossible, so this is funny, right? Or something like that. Let's see these examples. For example, causal understanding. In July, a city observed that ice cream sales increased and the number of drawings also increased. This is causality, so no. The answer is no, right? Because it's because of the hot, not because of the consumption of the increase of the sales of ice creams and the number of drawings. Also, the question 2 is the trophy will not fit inside the suitcase because it was too large. Yes, it's the trophy what is too large, right? Oh, the last one is more the cartoon caption that they suggest you a situation. A cartoon showed 2 penguins in an office conference room. One penguin is wearing a tie and pointing at a cell chart. Which caption is the funniest? So they say, our fees-based revenue model is melting. Why is this the most funny one? So because it combines the business setting with a penguin-specific context, like fees, ice melting, and the other option are generic and not explaining a cartoon singularity. These are complicated questions for LLMs, right? So what we try to do here are the benchmark that you can find it in a paper that is presenting this big bench extra hard dataset. And you can see the models until this moment and which are the solutions or the benchmarks by doing 0 shots, right? So we can see here the aggregation baselines, majority votes, self-consistency, and quantum combinatorial reasoning. You can see here that more or less we are beating some of them, but this is the most interesting. Oh, this should be 58, sorry, it's not well done. This should be exactly the same as here. No, this is the Cubo, sorry. Yes. The Cubo formulations improves a little bit, but by using the Cubo formulation, we increase more. This is the best solution that we have obtained by using GPT-4. But we can see that is not the highest increasement. For example, with quantum convolution plus llama, and llama alone, we can obtain like a 12%, 28%, and 3% on the questions, which is a lot because we are using exactly the same model, but using our strategy. It's true that the best one was with GPT-4, and we are beating O3 mini, O3 high. That is the reasoning mode of GPT, right? We are competing with it, and we are obtaining good results. In fact, we increase it using our reasoning mode over the reasoning or the inner reasoning mode at that moment of GPT. We increase it at 5%, 1.7%, and 8%, right? And in DeepSeek, for example, we win in these two, but we lose in that one, which means that DeepSeek has a very good reasoning model. Even the resolution is not the best one, improves a lot the baseline. Like is DeepSeek reasoning 1 is kind of much better than DeepSeek version 1. We also did another experiment that is merging LLMs, not only asking 20 times the GPT, but also asking DeepSeek and Llama, and the solutions are not that good. So it's better to try to improve the reasoning mode for each LLM by separated and not mixing them, because we obtain a very good performance in each one versus their own method. But when we're mixing, we don't obtain that increasement, right? Also, just to compare with other methods like majority vote, self-consistency, and the Kubo, and we see that we improve a little bit, well, not a little bit, quite a lot, by using Hubo formulation and not Kubo formulation. For example, this one is at 2%, but this one is close to 5%, and this one is also 2.5%. That is a lot because these questions are very, very complicated, right? This is another benchmark that we did because all this has been presented with simulated annealers, but we wanted to also do it with bias field DCQO, right? And the solution is very, very, very similar. I mean, that's why your question was very appropriate. We don't know if it's because quantum or not, but now it's not needed quantum. The thing is that the formulation is good enough, and we increase a little bit. That probably is because of noise or something, but it's not conclusive, right? So the formulation is very good, and the solver of a real quantum computer is competing or even better. So it's a good news, but it's not the cause of the improvement. The cause of the improvement is the formulation, right, or the methodology. Okay, here more or less is to see that the number of qubit needed or the number of reasons that we generate is related to the complexity, because these data sets, disambiguation and causal, we obtain up to 60% of accuracy, and the number of qubits is from 35 to 47, more or less, is the mean. But New York City, that is human, look, is 90. So the complexity of the reasoning modes increase a lot. And we keep only 22 selected, and we improve a lot, which is good because by using this optimization, we only keep in a mean 22 selective reasons, but we need 90 to try to solve it, right? Unique reasons. Also, let's go a little bit further because we need a demonstration also. Okay, just to mention this, for example, the difference from GPT-4 and O3 is 100, more than 100 times energy consumption. So if we ask 30 queries or 20 queries in this case, we are even improving the token consumption or the energy in a 20%, or in a more than only using the 20%. So it's 5 times less, right? Because we ask 0 shots 21 times, and only using one question for O3, it's 100 times more energy consumption. But if we ask 21 times, we are over, yes, the 20% of the O3 high. So we are increasing, or we are beating in energy. Here is not considering the backend, because the backend, if we want to solve in a quantum computer, is much more, right? So the conclusions are the ones. We did this first LLM plus a quantum bridge where we solved the problem with a real quantum computer, which means that we have the possibility to solve this kind of problems and also to increase the reasoning mode in actual LLMs. Hubo as a reasoning energy is a very good methodology because we prove it with a simulated annealer that is classical solver and also with a quantum solver. This means that it's solver agnostic. We can solve the problem with a quantum computer or with a classical computer. We see that we have an accuracy gain between the 3 main data sets from big, bench, extra, hard. Then we see that higher order is needed because we improve a little bit, well, quite a lot, the Kubo formulation, which is more or less the same idea, but by adding this Hubo or the 3 body terms, we see an improvement. And the future directions are trying to reduce these sequential or hierarchical reasons like tree of thoughts or combining different pipelines. We are now, yes, we have a little bit explanation about that, but I think we won't have the possibility to do it because the time is practically done, which is this one extension. So it's not needed. Let me do a small, if you want, presentation, right? How this works. For example, let's continue with football, but it's not needed. If you propose any question, we can change it. But who is the best player in football history? Need to answer one, because if not, he don't or she don't want to to solve it, right? So here you can add the number of LLMs that you want. Let's put 20. Here the up to iteration is in order to maximize the variance of the coefficients, nothing important. Here you can decide more or less temperature. If you put 0, practically the answers are always the same, so we are not having diversity, so let's put 1. And here is if you want a maximum number of reasons to keep, or we can use this threshold that I mentioned we can be more conservative or less. Let's put 40 just in this case to include more reasons. This takes a little bit because I create a demo here. It's not online, but it's taking just a little bit. So if you want to do some questions during this is creating the answer, it's also good.
All right, so we do have, I think, yes, both can solve it, but classical methods are currently more practical. Quantum computing has the potential to handle larger and more complex problems in the future.
Yeah, I mean, I think it's more in the future, yes. I think quantum computer can help when the questions became more difficult, right? If in the future they are very, very difficult, we will need to go for more reasonings in a high order dimensionality. So more than 3, for probably 4, 5, 6. This is the main idea that we have with this formulation. And if this happens, we should go for quantum computers. So actually, it's interesting that we can solve it bothly in both cases, so it's good. But in the future, I think it will be required, right? Let's see this example because it's Lionel Messi, but you can see here that he has picked 12 reasons, okay? This is the popularity at the end, that is if a question is included in this 25% of less energy things, and these are the ones that are discarded, right? So at the end, the final ones has only these 12 reasons and the question. And at the end is Lionel Messi. This is the thing. If you have more questions, it's also welcome because we have some minutes.
All right, so I have another question here.
Yep.
How do we decide the selection of Kubo-Hamilton or Hubo-Hamilton, and what is the specific difference between their formation?
Yeah, at the end, in the selection of Kubo and Hubo, I mean, it depends if you consider that it's needed or not. I mean, I will suggest always go for Hubo, not Kubo, because you can include these three correlation sides. And you have seen here over different problems and different datasets that are completely different, it improves in all of them, right? So if you can, I suggest you to go for Hubo because reasons in this case, if there are 3 reasons that appears constantly, probably these ones are very probable to obtain the final good solution. If you have only the most probable ones, it's like majority vote, it's not. But if, for example, 3 reasons appears in 5 questions, and in these 5 questions have the good answer, at the end the good answer is guaranteed, right? So that's why I consider that 3, even 4 or 5 body, if we ask more than 20 times, like 100 times, should be desirable, right? Because we can see this improvement clearly. He's at 2%, this is a 5%, and this is a 2.5%, which between them is practically a 10% of difference in the accuracy in the gap, right? The gap between the benchmark. Yeah.
All right, I'm going to give you one more question and then I'll let you continue your talk. If future quantum hardware becomes capable of solving much larger optimization problems, which part of the pipeline is going to benefit most? Candidate reasons, Hubo formulation, or reasoning data sets?
Yeah, Hubo formulation for sure. Hubo formulation I consider is the most interesting one if you want to use a quantum computer because it's the natively one. I mean, the good thing in quantum computer or the quantum computers is that the qubits interacts natively in an all order in a high order correlation ones, right? For example, it's true that the connectivity of IBM is 2D, but you can connect them by doing swaps. So you can naturally encode these high order optimization problems by doing swap layers that you can lose a little bit of control, but the fidelity is practically the same because now it's improving a lot on that. So for sure, high order optimization problems, I will say. Okay. So, okay, let's finish quickly because this is done. Just now mention you that we are increasing this formulation. Now it's much more complex. At the beginning, we only have statistical things like popularity, concurrence, or triple synergy. As I mentioned, the only thing that we add in a sense of NLP is the cosinus similarity about the reasons, is the only natural language processing thing that we add, but we can add more, right? So that's why we are now doing this weighted natural language Hugo formulation that I will explain here. It's much more complex, but at the end is more or less keeping the same as we had before, but adding also semantic relevance to the formulation, right? For example, the popularity reward favors the reason that appear more often is exactly the same. The variance penalty is exactly the same as the other formulation, but here this new coefficients starts to change a little bit. This is the cosine similarity of each reason to the question, which is interesting because sometimes the LLM tries to hallucinate and starts to talk about something that is not related to the question itself. It thinks so, but it's not true. And this is important to keep the focus on the question and not going out, right? Then also you can see these other coefficients that it's if the reason's name or not the answer at the end, because sometimes if the reason names the answer is better because probably this reason is definitely giving the final solution of the problem, right? So it's interesting to add it. Also blends concurrently, but also with natural language processes. Is more than only applying the cosinus similarity about the reasons, but also trying to see more language processing and try to include this. And yeah, more or less this is the idea. It's trying to keep the same formulation, but adding kind of semantically new context to the Hugo. And at the end, we are still working on it. I can tell you that we are not improving given the only frequency formulation, but we are working on that. We are trying to see if including this natural language processing or the semantical the importance to the Hamiltonian can help or not. Now, just for closing, we have created also some other AI tools in the platform for Kipu Quantum. This could have MCP is very interesting because what it does is it's an agent that can help you to go through the platform and to see which are the products that we have and which ones are interesting to solve a quantum machine learning problem. And this is the matchmaking agent that we include more or less all the knowledge that we have to this agent, trying to create you a step-by-step forward roadmap to solve your quantum machine learning problem or even optimization problem. I want to show you also this just for finish because it's very easy. You can go here to kipuquantum.com and you can ask for the problem. For example, I want to solve a credit risk problem, and you can ask. And it's kind of a chat, okay? And at the end, what you can have is a final report. Okay, for example, classifying. It's a classification problem. This can help you to create the strategy of solving a problem, a given problem, and also that propose you the way to do it, right? And this is, for example, very important. Tabular data sets. Yes. You can play a little bit around because this is online. So it's very interesting, mainly for companies that they don't know if quantum can help or not. This can tell you in a very honest way if your problem could be or not deployable in a quantum computer. Okay, so for example, 100 features, samples. You can more or less define your problem. Now we are doing it fast, but you can do it in a proper way. And at the end, I only want, see, for example, we want a 2% accuracy improvement that is more or less realistic, but it's possible. Okay, so this is, you can play around if you consider it's time, but yes, precision. This is good because you can see if the problem is in an honest way can be solved or not in a quantum computer, and it's very important. seconds. And then he creates a report that you can download it and you can start playing on it. Or even you can give it to another LLM and try to solve the problem. But also there are some products here in the Quantum Hub that can help you to solve the problem. So yeah, I think the presentation has finished. Also, I want to let you see here all the references that I've used, just to mention that could be interesting to pay attention on this chain of thoughts, which are the aggregation algorithms that there are, how the combinatorial reason can be done. Yes. Also for the ones that has asked why bias field is EQO, this is the paper, bias field digitized quantitative quantum optimization, is from Kipu, so you can also find it. You can find it in the website. Yeah, that's all. And let me show you how the report can more or less seems like. So here you have a final report that says, okay, your problem is an 82% good to solve it with quantum computers. You can download it and you can see why, right? This is a good tool to see how our products can help you to solve the problem. Yeah, that's it. So thank you.
All right. Thank you so much, Carlos. We are over time now, so I'm going to honor your time and let you be done. And then we will be sharing Carlos's recording and his slides if he can get them to us, and any other information on the LMS before the end of the day. So thank you again, Carlos. It was really great, and we appreciate your helping us learn together.